Okay, so let's look at question 2 of the tutorial. So we're asked to look at a reversible adiabatic compression of an ideal gas, and then we're asked to calculate some of the parameters. So initially we can immediately write that we have our heat is 0, and we're also given that it's reversible. So in other words, we know that it's actually a reversible heat. So reversible heat is 0. And then we remember that something very important about reversible heat, and that is actually the formal definition of entropy. So the entropy of our system is equal to the integral of reversible heat over T. And I mean, if that heat is 0, that means our system's entropy is 0. But also, because it's done adiabatically, it means that there should be no heat exchange with the surroundings. In other words, our surroundings heat, or Q sur, is also 0. So in other words, the entropy of the surroundings change is also 0. So what does that mean for our total entropy? Because that's what the question actually is about, total entropy. It's not really stated here, but if there's ever just a question that says delta S, then it means delta S total. I mean, it's the sum of those other two things. It means delta S is also 0, or delta S total is also 0. So we've actually has a bunch of things that are just 0 in the end. Right, so the concept that reversibly and adiabatically just covers a bunch of things at the beginning. So for a reversible adiabatic process, you have a bunch of processes that collapse, or not collapse, but are changes that are 0. And it actually makes a lot of sense, because if you have processes that are done reversibly, it means that there is no change in the disorder. Because change in this order means that you cannot you're not rearranging the system at all, because you are taking the system and you're doing whatever the change you are doing is that you can take it back in a way that you've changed it so that you can take it back exactly as it is. You've just changed some parameters in the system. For example, a good example is if you have a box with three marbles in it, and you have the box and or maybe 3 glued marbles in it, and you have the box and you shake it and nothing can really move around in it. You can heat it up and you can do whatever, but the marbles don't really move around and they stay there. You change the temperature or whatever of that, but nothing's changed in the box necessarily. If you had a box with 3 loose marbles in it, then you can change the box around there. You can't necessarily get back to what you initially had there in it. Very bad example, but you sort of get the idea. If you have something that you can change and you can't get back to it, you've done reversibly, and the entropy of the universe has changed. And once the total entropy has increased, you can't really get back to a previous state. And that's the main point here. So if something is reversible, then the total entropy is 0. So that means it is sort of like a chicken and the egg. But if the total entropy is 0, that means the process is reversible. So then we can go back to a previous state. So in other words, if something is done reversibly, the entropy is 0. The total entropy is 0. Okay. And now because it's done adiabatically, it actually means the system's entropy change and the surroundings entropy change is also 0. If the total entropy is 0, it could also mean that those two are just negatives of one another. So in other words, what is done to the environment is just the negative of what is done in the system, for example. But now because it's done adiabatically, these two values are also 0. Okay. Does that make sense? I hope it does. Gives you some more ideas in terms of that. So just remember, for reversible system, delta is total 0. Irreversible system, it will be larger than 0 because we can't go back to that previous state. Okay, enough about that. So what do we left to calculate? We left to calculate the work, the internal energy, and the enthalpy. So now, if we think about adiabatic changes and internal energy, so the definition of internal energy for adiabatic change is actually U is equal to CV delta T, or delta U. Delta U is equal to CV delta T for an adiabatic change. But we're given here, we have to work for, so that's for 1 mole. But we're given 3 moles here, and we have the molar heat capacity. So we just need to rewrite that. So in other words, we just work with NCVM delta T. Right, so just remember, if you just have CV, then you don't have to use the number of moles. If you have CVM, you work with the number of moles. So that's like a definition that you need to be aware of. So when you have an adiabatic system, then you can use CVM delta T for delta U. Okay, and that's something that we can use to calculate delta U. So we can quickly do that. I mean, that's something that you get from your theme 2, so it's not really that difficult. I mean, this is what, 3 moles, or 3 mole, it's 27.5 joule per Kelvin per mole. And delta T is 50 Kelvin, because we're going from 200 to 250. Yeah, so 250 minus 200. And this gives us 4.1 times 10 to the power 3 joule, which is 4.1 kilojoule. Okay. But we also remember from the first law that luckily our heat is 0, so this is just the work. So in other words, the work is also 4.1 joule. Yeah, so in other words, we already have the work. So we've covered work and internal energy. Now all that's left is our enthalpy. And of course, this is a general definition for adiabatic work. So adiabatic work is always equal to the internal energy. Sort of something that you can know, because it just means the heat is 0. So anyway, what are we left to calculate? We're left to it's the enthalpy. So enthalpy, we can do one of 2 things. So enthalpy per definition for adiabatic changes is similarly defined as the internal energy. It's equal to CPM delta T. Or there's a thermodynamic way that we can calculate it. It's actually by its fundamental equation, right? So we can do delta U plus NR delta T. We can also use that. But so let's use, the easiest one is actually this first one, because we can get CPM. So let's just draw a little arrow here to here. So what is CPM? CPM is equal to CVM plus R, which is then equal to that 27.5 plus 8.31145. It's roughly equal to 35.8 something joule per Kelvin per mole. Okay, and then we substitute that in there, and then eventually we'll end up with 5.4 kilojoule. All right, I think that is kind of nice, eh? It's actually a very easy question. Just the most difficult part is this initial argument for the entropy. Now, calculating the entropy. Well, not calculating it, just arguing why it is 0. But anyway, you can remember for an adiabatic reversible change, it's 0. But I won't necessarily. I like to ask you why things are what they are, and like just writing for me, it is 0, because anyone can learn that it is 0 and whatever. Okay, so that is essentially question 2.